Hello everyone. This is our presentation on the subject of graphical and generative models for machine learning. Our topic is image generation using variational autoencoders and generative adversarial network. On behalf of my entire team, I, Tanmay Vagre, will be presenting this presentation. For any generative model, we can say there are three steps in. First is the inference. It is finding the latent variable z condition on the given dataset. In other words, finding the probability of z given x, where x is the set of input images. Then there is a step of parameter estimation. It is all that maximizing log likelihood by backpropagation thing by which all the models are trained. And the last step is sampling or data generation. This step involves the generation of new data samples. Now let us talk about image generation. It is the process of generating new images which are similar to dataset images. There are many applications of image generation, but the most important is to reduce the sparsity of image datasets by generating new images that are similar to the datasets. Now let us talk about VAE. VAE stands for Variational Autoencoder. Basically, a VAE has two main components. One is called an encoder, which transforms the given image into a real valued latent vector Z. The other is decoder, which decodes the image given the vector Z. Both the encoder and decoder are some complex neural networks. There are two terms in the loss function of a VAE. One is the reconstruction loss, which accounts for how good the decoded images are. Other one is the latent loss, which or similarity loss accounts for the similarity between the probability distribution of Z given X and some prior distribution of Z, which usually is normal distribution with mean 0 and variance 1. Since Z is sampled from a distribution, so there is some random factor in Z. Due to this randomness in Z, we cannot train our VA using backpropagation algorithm. To overcome this obstacle, we can use reparameterization trick, which simply makes Z as the sum of two terms in which one term contains the random part. Because of this trick, we can train VAE using backpropagation. Now let us come to GANs. So GAN is the short form for the generative adversarial networks. Generative adversarial networks are a framework for estimating generative models via an adversarial process in which two models are trained simultaneously. In this one also, there are two components. One is the generator, which generates new images, and the other is the discriminator, which discriminates between the real and the fake images. The generator produces images so natural that the discriminator thinks they are from the real data distribution. Discriminator keeps getting better and better at distinguishing between real and fake images. Now let us see some facts about the datasets that we used. For this experiment, we used the MNIST and VIFAR10 dataset. MNIST contains 60,000 small images of handwritten digits for training and 10,000 images for testing. CIFAR contains 60,000 colored images that belong to 10 different classes like cat, dog, car, aeroplane, etc. All these classes are mutually exclusive. Now, the image that are you seeing on the screen are generated by our two models. Each and every image that you are seeing right now is not a real image. We can see that the images generated by variational autoencoder are somewhat blurry, while images generated by GANs are more sharper. On behalf of my entire team, I would like to thank you for paying attention to our presentation. Now, I request my teammate Bhargav to take control and show a quick go-through of our code.
Hi, this is Bhargav. Now let us just skim through our implementation on variation autoencoder and generative adversarial networks on Cipher-10 dataset. Due to lack of time, we'll have a cursory look on the implementation. This is the importation of the necessary libraries. We use the TensorFlow architecture for building the encoder and the decoder. This is the event. This is the data pre-processing and cleaning a block of code. Now we have plotted one of the example training images in our Cipher-10 dataset. It is a colored image, as you can see. Therefore, it has R, G, and B layers. This is another grid of images. In this block, we have defined the variation autoencoder architecture. This is the encoder block. This is the encoder architecture. Now this is the decoder block. And this is the decoder architecture. We have to ensure that the decoder's output is 32 cross 32 cross 3. That is the dimensions for the Cipher-10 dataset. For the gradients to pass through, this is the sampling methodology. That is the reparameterization trick. We sample an epsilon and then transform it using this. Now to combine all three, encoder, sampling, and decoder, we create a class that is VAE, superclass. We can say this is the model summary, that is the VAE summary consisting of all three blocks. This is the Adam optimizer, their learning rate. To keep a track of the losses, that is the total training loss, the KL divergence loss, and the reconstruction loss. We have created these functions. It checks all the three losses epoch by epoch, which gives us an output of such. And then this is the training images, like the training loss that we have plotted. This is the reconstructed output of the decoder. This is a grid of such reconstructed outputs of the decoder. And also we can visualize the mean and variance plots as a 3D image. This is an interactive plot. It allows us to play with it. This is for the mean, and this is for the log of variance. This ends our implementation on variation autoencoder. Let's start our discussion on the implementation of GANs on this dataset. The code that we are discussing here is a shorthand form of the original code because of the lack of time, and all the original results that we have of our implementation are discussed in the report. So we start off with importing all the necessary libraries to define the discriminator and the generator. We set up the discriminator as this architecture. The input shape to the discriminator will be a 28 cross 28 cross 1 image. That is a grayscale image, which is the usual shape of an MList dataset. The output will be a 0 or 1 value, which gives us if the input to the discriminator is a fake or a real image. This is the generator. The first layer of the generator will have a latent number of dimensions that we set a prior, and the output will be a 28 cross 28 cross 1 image, which will correspond to the generated MList image. Then we define the GAN as the combination of the generator and the discriminator. This is the real sample loading. The generated sample, the generated latent points is the output that we get through the generator. Sorry, the generated latent points is the generation of the latent points, and the generated fake samples is the output of the generated model. when we input the generated data images. We here train the both of them together. Uh, the train on batch method gives us a very easy way to actually shuffle between the min max objective function with respect to the generator and the discriminator. And here, these are the data dimensions and all the function calls. This is the shorthand form of our code. Thank you.